All right. Without further ado, Chris.
Yeah, thanks, Jerome. Really happy to be here with you today to tell you a little bit about our work in the space of electrochemical separations. This is the second time I've done a Gamry talk, I think, in 3 or 4 years. And we've worked with Gamry instruments for a long time now. So, all the data today was collected on Gamry instruments, but happy to be with you here today to tell you a little bit about our work. Quickly, I just want to acknowledge the Office of Science, Basic Energy Science, the separation science program that supported the results that I'll be presenting today, and the people who did the work here, primarily Tamay Kulkarni, Bin Yang, Bharat Tremont, Mario Ramos Garces, and Chile, and Aliyah Al-Daman, and the variety of different collaborators who have supported these projects in this space over 5-6 years now. So my presentation today, I think how this all started, I wrote an ECS interface article on electrochemical separations for sustainability that came out last spring, and it caught Jerome's attention. And it's an area that's attracted a lot of attention in recent years and garnered a lot of momentum. And so I'll give a little background on, all the different applications, some applications you can use for electrochemical separations. What are the different technology platforms for the separations and the modes of action that enable selective ion separations? That's probably the most interesting area right now. If we have a mixture of ions in solution, how do I take one ion versus another? That other ion could be like a valuable metal, it could be a bad actor in the environment. And so we're really interested in the science of that and engineering solutions to solve those type of problems. And to do that, the results will tell you a little bit about like determining ion activity coefficients within membranes. And then at the end of my talk, we have 2 short stories on selective ion separation. So one where we're looking at recovering critical minerals like copper and lithium from mixtures. And then on that one, we use a bipolar membrane with selective electrodes to enable those selective separations. And then the latter part will be on these mixed matrix composite AEM materials for selective phosphate removal from a mixture. So there's a plethora of applications that electrochemical separations can service. The most mature area is water desalination. So you can make potable water, drinking water. Where it's really found today, just because of the advent of reverse osmosis, is making electrochemical separations really service making ultra pure water like 18.2 mega ohm water. Electrodeionization is a process used to do that. And so today I'm not going to talk about, removing all the ions out of water solutions. And, a lot of people try to compare like the electrochemical method versus the osmotic method. We're not going to talk about that today. Again, at the end of my talk, we'll talk about nutrient recovery. So we can think of, people who apply fertilizers to grow crops. There's excess fertilizer with ammonia and phosphate. They run off into the water. This can pose a lot of different environmental problems. There's also interest in, recovering the phosphate and ammonia to be recycled, reused in fertilizers. That's part of like a circular economy initiative. There's interest in gas purification, so we can think of direct air capture, removing CO2 from the atmosphere. We do some work in hydrogen purification from gas mixtures. I won't be talking about that today. We've done some work in recovering organic acids from processed biomass. These organic acids are good building blocks. Biomass is, sort of a more sustainable way to get the organic materials we need for our modern society. But like what we'll talk about a little bit is in the critical mineral space, mainly copper and lithium today. But there's other critical minerals that are important, such as rare earth elements, platinum group metals, et cetera, et cetera. So as you can see, electrochemical separations can really touch upon multiple different areas. And so this ECS interface article that came out last spring highlights all these different areas. And so this image is for CO2 removal from air using a shorted electrochemical membrane. So critical minerals and materials or really should just say critical materials are paramount for the energy transition. So we're going to see a lot of electrification, whether that's for like powering our homes or powering our vehicles. But there's also a lot of interest in electrifying manufacturing to reduce greenhouse gas emissions from that. And so all this electrification is going to need these critical materials. So copper is a really big one for transmission and distribution. Iron, electric steel is like this iron with silicon. Batteries. This is for energy storage and conversion. So there could be like flow batteries, but you could also use conventional lithium-ion batteries. So you need lithium, cobalt, nickel, vanadium, etc. Fuel cells and electrolyzers. So you think again, hydrogen at scale, like platinum group metals are really paramount to electrolysis. And so this was a report that came out from the Department of Energy last year highlighting, these mineral materials here, these elements, how important are they for this energy transition, this electrification, and then what is the supply chain risk today? Like, do we currently make these within the US? If so, how much, or how much do we make them worldwide? And you can see here, there's a lot of these materials on this list here in the red, that means they're really important, and the supply chain is currently risky. And so we sort of need to enable new processing technologies that enable maybe the mining or recycling of these materials. And within those processing technology, separations is really important. It's part of the refining process. So just I'm not going to go through this image in a lot of detail, but if we it's not a monolith like how we collect lithium from different mixture solutions. Like there's different types of brines, like solar, geothermal. But the bottom line here is that the current processes are very lengthy. We might have these evaporation ponds to concentrate these ions in solution. We'll use like solvent extraction, absorption, maybe some like osmotic-based membranes to sort of purify and concentrate these lithium salt solutions. And then we often have to use acid and base. And so the bottom line is this current process is, it's lengthy and generates a lot of chemical waste that isn't good for the environment. And so what I'll show you on later in my talk is we have an electrochemical method that can reduce the amount of chemical waste in collecting lithium from brine. But lithium, as you can imagine, is extremely important. It's a 400% increase expected within the next 5 to 6 years. And what we'll be showing later today is how we make lithium hydroxide, which is the preferred precursor that battery manufacturers want to use for making battery materials. And the alternative is lithium carbonate, but there's more lithium per mass in lithium hydroxide than lithium carbonate. So, all right. So now I want to tell you a little bit about, the different platforms that are available to enable these separations. And so the first one is this electrodialysis platform. And this is a common method where you would feed in a brine solution, sodium chloride, and you take all the ions out of water. This is unlike an osmotic method where you're really removing the water out of the brine solution. So you have these electrochemical reactions at these terminal electrodes that force an electric field on the system and that force the ions to migrate across these repeating pairs of cation and anion exchange membranes. And so you get a purified stream and a concentrated brine stream. The problem is in these purified streams over time, the resistance becomes so large, it's really hard to get ultra pure water. And so what you can do is put ion exchange resin particles within that diluent compartment held together by a polymer binder. We call this ion exchange resin wafer. And this can augment the ionic conductivity within this wafer stream. And then, the resistance of the cell is reduced and you can get this ultra pure water. So other methods, you can have these, 2 electrodes. You can have a solution that's flowing through it. And you can do electrodeposition. So maybe you have some type of valuable metal ion, like say copper on here. Then you can reduce the copper here at the negative electrode and plate it on this electrode. And then you get the anion just to absorb in the electrochemical double layer on the other electrode. So electrodeposition is also a very good method for doing separations. And so what's sort of nice is if you had a mixture of metals, right? You can use this electrode potential, like one potential that does the reduction of the metal where the other potential doesn't, to enable a selective separation. There's very similar to these flow diagrams, which are electroabsorption methods. So you have these porous electrodes. We'll talk about the modes of action later on that enable selective separations, but you put an electrical bias on these electrodes and you get the cations to absorb in one electrode and anions to absorb in the other electrode. Because of like ion charge pairs and screening, if you put these ion exchange membranes here, you can prevent co-ion absorption. And so you get greater electrical efficiency with these membrane versions of the cell, whereas this system doesn't have any ion exchange membranes. The advantage of the system with no ion exchange membranes is just basically cost, because ion exchange membranes are quite costly. There's also electrocoagulation is another method, and there's various embodiments of this method, but you can basically oxidize a metal. This metal could chelate with a species to precipitate it. Then you could have flotation or sedimentation to collect it, or you do water reduction at the cathode, generate hydroxide. This could react with different metal ions within the solution, make metal oxides, and again, you can centrifuge or as a way of separating out the different metal ion species collected from the solution mixture. So one area that we've worked in here, just to illustrate the importance of selectivity, is with Martin Bazant and his team at MIT. They've developed this method called shock electrodialysis. And so it's a single compartment that has a splitter here at the end, and you have a porous conducting medium here. So historically, they've used borosilicate glass frits, which don't have really a lot of formal fixed charges on there. And we substitute it with these ion exchange resin wafers, so those ion exchange resin particles in a polymer binder. And you operate this thing over the limiting current. So limiting current is that you apply more voltage, but your current flatlines. But if you keep applying more voltage, you'll get over that limiting current. So that's what we call the over limiting current. And what we sort of observed here is that if we had these heavy metal ions, so you can think of like a Flint, Michigan water situation, where we're looking at the retention selectivity of these heavy metal ions over sodium. So there's brine solution in the solution here. And what you want to do in this concentrated effluent stream is get more of these heavy metal ions together. So this ion exchange resin wafer can increase the retention selectivity much higher. It reduces the ohmic resistance in the cell because the ion exchange resin particles have these fixed charge groups. So when you're operating over this limiting current, right, you have electroosmosis, ion surface conduction, and that create these shock waves that sort of enable this pseudo-selective separation. So we're not separating these individual heavy metal ions individually, but we are separating it from sodium chloride, which is sort of a benign species, whereas things like cadmium and mercury are not. So the modes of action, so like in porous electrodes, we can think of, okay, we want to take ion A over ion B, so the porosity of this material, the hydration energy extent, like when you shed its solvation shell, the electrode property materials could affect that perhaps, and that would enable a selective separation. Chemical affinity, right? You could modify this electrode material where it prefer one ion versus the other. And then you could exploit the ion mobility difference where you've modified the electrode in such a way where ion A is going to move faster across it than say ion B. I'll tell you a little bit about on the next slide, these redox active polymers. This is where we change the oxidation state of these polymers. And then that can enable selective separation. So the change in oxidation state can be done at a given potential. You can engineer these redox active polymers like molecular engineering to have different molecular interactions, such as dispersion and hydrogen bonding that would enable a selective ion separation. And then we've talked previously about electrodeposition already. So colleague of mine, or not colleague, but friend in the area, Xiao Su at University of Illinois at Urbana-Champaign. These are these redox active polymers. So you sort of have like this temple group here on a polymer backbone. What he did in this nice JAX paper is add a repeat unit with a perfluoral group here. And what they were trying to do was remove perfluoral butonic acid, which is a PFAS type of compound. So here you're going to get those van der Waal interactions between the PFAS compound and this redox active polymer. And then, right, like if I apply a positive potential on here, I can oxidize, release these electrons here from it, and then I'll get this positive group here. And this normally, if it's under base solution, this will be an anion here, and this positive group in the anion can absorb the perfluorinated compound. So this is this electrode before absorption, before we do the oxidation to make this compound. Then when we do it afterwards, these are EDX images here. The fluorine is red, so you can see this PFBA absorbed onto the surface. Here they absorb at 0.9 volts versus silver chloride reference electrode. They have the largest uptake. And then you can move the potential in the negative direction, right? Where then you can reduce it back to its negative state. This PFAS compound is released back into the solution, and then you'll get sodium ions, which is here represented in purple, absorbed onto the electrode. And of course, PFAS, very hot research area right now, just because these forever chemicals found in the environment accumulate in our body and have a myriad of health risks to us today. So a lot of interest in trying to remove these things from the environment. And so that's another area, environmental remediation, that electrochemical separation touches. So now I'll tell you a little bit about ion exchange membranes. What could we do on the membrane side as opposed to the electrode side to enable selective ion separations? So the membrane chemistry itself, like you could try to do something very similar with redox active polymers, alter the molecular interactions to enable a selective separation. The valency of the ion will matter quite a bit here. So usually the rule of thumb is like you have electrodialysis membrane, ions of the same size and valence, like conventional ion exchange membranes today cannot discriminate between those two ions. So a lot of times you'll see like surface engineering of the membrane, like you might have some oppositely charged polymers here. This is an effective strategy for promoting monovalent ion transport and rejecting divalent. So you can get that type of separation using this approach. And then I'll tell you a little bit later about composite membranes. So this is sort of inspired by some work that Jeff Long and David Jasby at UCLA have done, where you can put these certain particles in here that have a very high affinity for a certain species within the membrane. And you can integrate this into an electrochemical cell for selective ion separations. So the final modes of action for selective ion separations is pH adjustment. This is pretty important. And what we're really interested in is in situ pH adjustment, as opposed to, adding acid and base externally to the solution. The acid and base, that means you have the chemicals on site. There's a large energy use with that acid and base. So if you think caustic soda, you have to think chloralkali process. And so this is some work done by Alan Hatton and his team at MIT. So they use this redox active polymer to capture chromium-6. When they do that, right, they do water reduction here at the opposite electrode, where they generate hydrogen and hydroxide ions. And then after they've captured the chromium-6, the redox active polymer here is ferrocenium. So they go from ferrocene to ferrocenium. They'll reduce the ferrocenium to ferrocene. That'll release the chromium-6. You'll have water oxidation occur at the other electrode. So instead of generating base and hydrogen, you'll generate oxygen and acid. This acid can convert this chromium-6 down to chromium-3. So we can use these Parbet diagrams to sort of inform a separation strategy. And the thing with chromium-3 versus chromium-6 is that it's much more benign in the environment. It's not as bad as chromium-6. So, you could, of course, do the pH adjustment, as I said before, by externally acids and bases, but, there's some downsides to that. Can you do the in situ pH adjustment within the cell? And really the two ways to do that are these Faradaic reactions. So we can think of water reduction or water oxidation. This would generate base and acid respectively. You can do oxygen reduction, to generate hydroxide ions, or if you want to feed in hydrogen, you can generate proton source carriers. So an alternative way are these bipolar membranes. The thing with the Faradaic reactions, not all cases, but especially with the acid cases, you tend to use platinum group metal ions, and you're generating gas. That can cause a problem within the cell because now you have a biphasic mixture of liquid and gas. These bipolar membranes, you have water that migrates to the interface of the anion and cation exchange membrane, undergoes dissociation, and can generate hydroxide and proton ions. And then later I'll show you on that you can run these things in forward bias mode, where they act as a proton and hydroxide ion seek, and that can also adjust the pH of your solution. So now I want to go into a more fundamental aspect of electrochemical separations, and it really relates to electrochemical equilibrium. And to understand this equilibrium, we need to understand ion activity. And to understand ion activity, we need to know activity coefficients within these membranes. And so we'll go over theory, experimental methods, and machine learning here. And if we had a liquid mixture, so we got sodium in here, we got chloride, we've got lactate anions, and we talked about process biomass, like how do we take organic acid anions, lactate, you can polymerize this to polylactide, renewable plastic. How do we get this membrane to say take the lactate versus say the chloride? And so what you're really interested in is this counter-ion selectivity term. It's almost like a permeability parameter where we want to take ion I over ion J. And if we look at this, solution diffusion model, we have two components, which is this partitioning factor. This is informed by thermodynamics. And then you have this ionic mobility ratio, which is really governed by the diffusion of the ion across the membrane. And if we go look at the partitioning factor here, it's really the activity difference or ratio between the species I in the membrane versus the solution over species J in the membrane over the solution. And these activity values are informed by the activity coefficient multiplied by the concentration. And so what we're going to talk about here in this section is really, how do we get these non-ideal coefficients, these activity coefficients. And so what are they, right? So we have, if we look at our change in Gibbs free energy, the actual one versus what we can calculate from the ideal, knowing the concentrations, the difference between these two values are known as the excess Gibbs free energy. That's the non-ideality. And if once we know this excess Gibbs free energy, or if we know the activity coefficient, we can get the excess Gibbs free energy. It's this non-ideality that's wrapped up in this activity coefficient here. So if we look at Prosnitz's book and we look at the mean activity coefficient, that's what M stands here, mean activity coefficient. And it's sodium chloride and water. D is this experimental data. So one common, model is the Huckel model, right? And then when you get to an ionic strength over one molality, right, you can see that model fails to predict the experimental data. A more sophisticated model is this Pitzer model. It's a semi-empirical model, and it can be even more elaborate with more more parameters here. But it's really complex as I show you. And the thing with the activity coefficients, why they're so difficult to determine from theoretical models, is that you have multiple molecular interactions, long-range interactions and short-range interactions that will affect the activity coefficient. So here's the Huckel model shown here. It's actually a pretty straightforward model. This is the ionic strength, this concentration of ion solution, and then this B and a superscript not term would be like some known parameters for that salt value. This Pitzer model, right, this more elaborate model, you have some function here of the ionic strength, and then you'll have these expressions here. There can be more of them, and these are virial coefficients here, lowercase lambda and capital case lambda. And so what you're going to need to know is the virial coefficients of the ion in the solution to get the Gibbs excess energy, because once we have the Gibbs excess energy, again, we can determine the activity coefficient. So our area in this work was motivated by some work done by Benny Freeman and his team at UT Austin. And they were interested in coming up with these activity coefficient models. And they started looking at, what had been done for polymer electrolytes. And so Gerald Manning, in 1969, he was interested in the colligative properties of polyelectrolytes in solution and why their activity was lower, for a given concentration compared to salt ions in solution. And so those polymer chains in solution, you can sort of think, could you extend this model to like a polymer membrane or a thin film? We study thin films here, and I won't get into why we do that, but part of the reason is we can control their microarchitecture. And if we put, say, a very, very dilute solution of salt on top of this film will absorb some water, under very dilute conditions. This activity coefficient will be closer to 1. But when we look at the concentration of the ions within the film, which is much higher, we have an activity coefficient that's very, very low. And so what we're interested in are why are the values of these polymer electrolyte films, why are their activity coefficients so low? And so Manning's theory argued that when you have a linear polymer chain and you tether these ionic groups on there, that the charge density is so high and that these ions condense, you can sort of like, they're not dissociated, and thus don't really contribute to the overall activity of the system. So that's sort of the idea and theory here a little bit. So he came up with a very simple, elegant model. Doesn't need adjustable parameters here, and it's really based on two different things. One is this Greek letter here. I think it was psi, but we call it the Manning parameter, and it's a dimensionless parameter. It relates the Biram length to the average distance between fixed charges, and then this x value here, which could be like the co-ion inclusion within the film. And this Manning parameter, this Biram length, this is the distance that you can separate a positive negative charge using the available thermal energy in the system, right? So more energy in the system, you can separate opposite charge particles further and further. And you normalize that Biram length distance to the average distance between fixed charges, right? So for a monovalent salt, this critical value would be 1. But like if you have condensation occur, say like half of them are condensed, a Manning parameter might be 2. And so we can run experiments where we know the activity coefficient of the ions in solution, right? We can use that Pitzer model. We know the concentration of the ions in solution. We can make measurements of the concentration of the anion and cation within the film, and then we would be able to get our activity coefficient, and then we can compare this against the model. And so Jovan Kamchev, who worked with Benny Freeman, who's now a professor at Michigan, showed that this model worked pretty well for an anion exchange membrane. So this is our external solution concentration. This is the activity coefficient within the membrane, benchmarking events against some other models shown here. Their team, Benny Freeman, his team, they've extended this model further. So this is actually sulfuric acid within naphthalene. So this is like, a divalent here, a divalent anion, and then 2 monovalent cations here. And they show that this model can be quite effective. Here you're looking just at the activity coefficient of the sulfate anion within the membrane. In this correction, what they do is have this alpha value here in addition to that Manning parameter and that co-ion inclusion value. And this alpha value really describes the fraction of ion charge pairs within the membrane. So those are, the sulfuric acid within the membrane that haven't been dissociated. And so they run experiments to determine that value. Once they determine that value, then the model does a pretty good job at getting at, this case is the amount of sulfuric acid absorbed by the membrane, but you can calculate the activity coefficient from that. So in our work, what we were interested, does this microstructure architecture of the film affect activity coefficients? So we looked at a random copolymer electrolyte. So we have non-ionic repeat units mixed with ionic repeat units, and we have a block copolymer system, so a system that's been microphase separated. So this black line is the block copolymer, and we saw Manning's theory, the Stahn-Manning model was like a spot on, right? Like it predicted the data very, very, very accurately. And I think that makes sense because like in the phase separated domains where you have the charge ionic groups, that is a little bit more like a polymer electrolyte in solution to predict colligative properties. In the block copolymer, right, like you have the ionic groups randomly distributed through the repeat chain. And so you'll have areas that are well hydrated and areas that are not hydrated that well. And so Manning's theory doesn't seem to do as well here. What's interesting though is because the ionic groups in the random copolymer electrolyte are spread further out, you get a smaller Manning parameter, which indicates less condensation and hence a higher activity coefficient. We've looked at other ways of measuring activity coefficients, and so this is using some of the tools available to us at the Advanced Photon Source here at Argonne, but this is time when I was an academic, where we have a very, very thin polymer electrolyte film. We put a liquid droplet on there so we can use those high energy X-rays to get through the liquid droplet and look at the Q spacing, the scattering peak here. We can see the first order peak here. We can't see the second, third, fourth, fifth order. We usually see up to 5 orders with block copolymer electrolyte films. Like we just have a gas here, humidified air as opposed to a liquid water droplet, but this method still works well. And then if we were to zoom in on that first order scattering peak, depending on the concentration of the salt ions within the liquid droplet, right, we can change the Q spacing. So in this case where it's really more dilute, we get a lower Q spacing, which means a larger domain. And then as we feed in this more concentrated salt solution term, right, we dehydrate the film, the Q spacing shifts to the right. That means the domains got smaller. And we related this GI SAX data to a QCM. So this is stuff, this is actually collected on the QCM from Gamry. And we can look at the solution uptake from QCM versus GI SAX for the same material. And what we're interested in is this transition point. So like as we increase the concentration of the salt solution of the droplet, right, we get, constant solution uptake till we get to this transition point where we move from this osmotic regime to this condensation regime, right? So now we get more co-ion inclusion, we get more salt ions within the film, we get charge screening, we see dehydration because the liquid droplet behind it, it's, wants more water. This is where the solution uptake and the periodic spacing goes down at this transition point. And so this transition point, it's not a really good accurate way for looking at activity within the film, but it gives you a proxy. And what you can see here, it's about 0.05, 0.06 molar. And this material would have a molarity of 1.9. And so it tells you that a large fraction of these ions within the film are, quote unquote, condensed, right? Or not contributing to activity. So this is sort of this idea, right? So dilute, swelling, non-dilute, dehydration. And so, we didn't make this up ourselves. Nitash Basara had applied these ideas and techniques to bulk Nafion membranes here. So he did some Sachs experiments with Nafion with sulfuric acid. So again, as you increase the sulfuric acid concentration, you're looking to that transition point where it's swollen and then it starts to deswell. So this is the domain spacing and this is the solution uptake. This was measured gravimetrically. And they also observed that a fraction, the fraction of ions that are condensed within the system is quite large from these two methods, 0.92 versus 0.98. They also looked at an ion uptake measurement that, gave them more like 0.72. But what they were really surprised to see is that they argued that, a large contingent of the ions in Nafion are quote unquote condensed. So this idea that, okay, these condensed ions don't contribute to activity, like that seems like it would hinder conductivity, but our work and other people's work have notably shown that it's actually the condensed ions that transport a lot faster than the non-condensed ions within the film. So we've extended these things. So this red line is the random copolymer electrolyte. So this is the solution uptake. We study block copolymer electrolytes where we control the molecular weight distribution of the polymer film. So we get different periodic spacing values. And what we observed in the cases of all the block copolymers is that this transition point didn't matter how big the domain spacing was, whether if it was 20 nanometers here or 80 nanometers here, that this transition point occurred at the same place. And this was verified by the QCM solution uptake experiments as well as the GI-SAC scattering experiments. However, the random copolymer electrolytes, that transition point occurred much later. That had a much larger activity within the film. And that jives with what we showed earlier from the activity coefficient values we determined from where we measured the concentration of ions within the film for a given solution concentration it was exposed to. So we've collaborated with Revati Kumar at LSU Chemistry, and she runs MD simulations to help provide insights into solvation and water cluster size in there. And so things that she'll get out of here like mean square displacement or the radial distribution function. And so notably, if we had a block or random copolymer electrolyte, regardless of the configuration, most of the counterions are in the first solvation shell from these radial distribution functions. So we really find here that, this isn't a very good method to determine like, okay, do we have a more dissociated ion versus another? Interesting what she showed though is that, water cluster size. So even though this block copolymer system, right, has lower activity coefficients, more condensation, it has higher conductivity. And the reason is that it has a lot more water molecules in a given cluster than say the random copolymer electrolyte. And so water is hydration is really important for mediating ionic conduction within these films. So, we like working with people who could do MD simulations, but, they're costly and there isn't a very good way to relate the outputs from the simulation to activity coefficients. And this is where we think machine learning can sort of fill this gap. So we had a paper come out last year where we did two different things in the paper. One, we wanted to use machine learning. We generated molecular fingerprints of the ion exchange membrane material, right? Like Morgan fingerprints. And then what we wanted to do is the machine learning to output the MD descriptors that you would have from normal MD simulations. So could we have a machine learning method that would give us the MD descriptors for a given ion exchange membrane material without necessarily running the costly MD simulations? Then what we wanted to do is then do another form of machine learning on top of that, where we relate the MD's output descriptors to those activity coefficients that are really important for selective ion separations. The sad part is there is not a lot of data in the literature of ion exchange membrane materials or thin films where there's available activity coefficient data. So it's not like a lot of people are going out there making these measurements. But we found 13 different IEM materials where they did make those measurements. Associated with each of these membrane materials, we have the ion exchange capacity value. That's the number of charge groups on the material and water uptake. We then, we did solvation descriptors from each IEM material prepared via Morgan fingerprints. I'm not going to get into that today. But what we'll show, even though with this limited data set here, 92 data points, doesn't scream machine learning, we show that it can still be quite effective. So here, what we're looking at is sort of a heat map of the pairwise relationship between the membrane properties and MD solvation parameters. These are all like, A and B. Here's concentration of salt, number of water molecules per ionic group on the membrane, and then the rest are these MD descriptors here. I'm not going to go through each of them here, but what I want to tell you is that we found a positive correlation that related, the lambda value. This is number of water molecules per ionic group on the polymer backbone, and the activity coefficient. So that's from the Spearman rank correlation. And then we saw a negative correlation between the radial distribution function peak height between the membrane farther charge group and the oxygen, the water molecule. So this is sort of what, the machine learning can sort of identify, okay, what are these MD descriptors defining, how are they relating to the activity coefficients? In terms of the machine learning methods for MD descriptors, we looked at 3 different machine learning methods: support vector regression, artificial neural network, and random forest regression. Here, overall, they seem to do pretty well, a good job of predicting the MD simulation outputs from descriptors. So this is for the training set, and this is for the test data set here. I think we largely rely on ANNL and SVR because they give the lowest mean absolute error value here, this MAE. And, here, I believe I can't remember which color is which, but I think the yellow here is the training data set and the purple is, I think yellow might be the test data set and the purple might be the training data set. But the bottom line is this ANN is really effective for predicting these activity coefficients from what is measured and predicted. So again, right, like you can dial in whatever membrane chemistry you want, use the Morgan fingerprints, then we relate, what the MD simulation outputs that would come from those structures there, and we can relate those MD simulation outputs to the activity coefficient. And then the shape analysis here can, reveal the MD descriptors that have the most important features. So B and G here, which is this peak position of the RD radial distribution function of the counterion oxygen of water versus the peak height of the radial distribution function of tethered charge. So for this part of the talk, I know I'm running out of time, but we started late. So, if you can stay with us a little bit longer, I appreciate it. I would just say accounting for activity coefficient IEMs is challenging. We talked about some of the models available to do that, but is really necessary for understanding partitioning behavior and eventually achieving selective ion transport membranes. So, the Manning model, it's pretty nice, but it's too simplistic in some ways. And so we usually have to introduce corrections to it. And then, there's semi-empirical models, but, they require a lot of data, such as virial coefficients to substantiate them. This is where we think machine learning can be an effective tool here, even on small data sets to predict those activity coefficients. So one final thing I'd say, this was a really nice paper that came out from Xinghong Lin's group at Vanderbilt last year. Everything I told you right now was just a single salt component in water interface with a membrane. But what we want to do is discriminate one ion versus another. Could we use the, Manning-Donnan model or another version called the Donnan affinity model to do this? And the answer is sort of yes. So the dark lines is this extended Donnan-Manning model here. This normal dashed line is Donnan affinity, and this dashed dot line is just the Donnan model. So the first point is the Donnan model, which is, ideal solution, it misses the mark by quite a bit. So we talked about the Don and Manning model and this Don and infinity model. This Don and infinity model works pretty well. These are the parameters you get from the Don model, but you have this correction term for this excess chemical potential excess energy value here, or chemical potential excess value. This is the affinity of one ion for the membrane versus the other. And so if you can experimentally determine this value, then you can get this selectivity coefficient value. Perhaps we can use machine learning to do that. This extended Don and Manning model, right? What you need to determine is the fraction of the uncondensed ions for ion J versus the uncondensed ions for ion I. And then you have to know this Manning parameter here. And so usually you'd have to determine this value, this condensation energy difference value between the two ions here experimentally. And then this model tends to work, but this is a relatively more complex approach. But it does seem like, a lot of progress is being made in the area. So it's quite exciting. All right, two quick short stories on selective ion separation. So we're going to go from the more fundamental type of research to more applied. I guess that's what you can do as a chemical engineer. So we were interested in running, membrane capacitive deionization. We're one of the first groups to do this with a bipolar membrane to do in situ pH adjustment. So what we'll have here is we can apply a potential difference between the cell, get it high enough where we have water dissociation within the membrane. Hydroxide ions are absorbed here in this positive electrode, and the protons migrate into this solution, generating an acidic solution. And so this acidic solution might be useful for enabling a selective separation. If we can change the configuration where we put the bipolar membrane on the other side, where we can generate an alkaline solution. So if we feed in a sodium chloride solution, right, we start to ramp up the potential for, configuration A and B around here, around 0.75 volts. We start to see, okay, if we have configuration B, we get an alkaline solution. And if we have configuration A, we get an acid solution, as one would expect. And then our first demonstration for this, we wanted to do, something pretty easy. Could we take copper out of a model wastewater solution? So we just have copper chloride and sodium chloride, but maybe much smaller amount of copper chloride versus sodium chloride. So a 4-to-1 ratio. And we know, right, if the solution's alkaline, those copper ions, if you reduce them, you're going to make copper oxide. This is a passivating material. This will prevent current flowing through that electrode. But if you keep the solution acidic, you should plate metallic copper. So this group here, what they did is show that, yeah, as you make the pH more acidic, they were able to increase the copper removal efficiency in a non-BPM MCDI unit. So we showed that it works, right? So here's our conventional MCDI versus BPM MCDI and how much copper we removed from this feed solution of 1,000 ppm NaCl and 250 ppm copper chloride was much higher. And then we could just see it visually, right? So when we generated that acid environment using the bipolar membrane, we get nice looking metallic copper here on the carbon cloth electrode. Whereas if we didn't do anything, the pH tended to be more alkaline and you get copper oxide, which are these blue precipitates on the carbon cloth electrode. So I showed you the steady state value, right? So this is the effluent value here. But now what I want to do is show you what happens during charge-discharge cycling. And we discovered something unexpected. So these are two commercial BPMs. So we're charging here, we're making acidic environment. That's where you'd want to do that copper plating. And then, then when we have to discharge the cell to regenerate the electrodes, we thought the pH would return to somewhere around pH 7, maybe 8. But no, it went alkaline. It was starting to climb to pH 10. We didn't understand why on this discharge cycle we were generating, we were getting this pH inversion effect. We're making alkaline pH. So my student, I'll just go quickly through this. We thought, well, maybe it's these hydroxide ions that are stored in here. They can go across the bipolar junction here, across this cation exchange layer and get into the process stream on the discharge. But we did this H cell experiment with sodium chloride and sodium hydroxide, and we never saw any hydroxide ion leak through the BPM. So we, scratched that method. For my time working in pharmaceutical industry, for different reasons I won't get into, if you leave behind one ion, say a sodium ion, in the water, because of electroneutrality, the water is going to have to shift its distribution of proton or hydroxide to accommodate the sodium ion so that you maintain electron neutrality. So here we just had a cation exchange membrane. We had two different concentrations of NaCl. So we have this chemical potential to drive the sodium across this cation exchange membrane here. And as the sodium increased in this lower concentration cell, we saw the pH increase here. So as you release these cation groups in here, these hydroxides go here. This water, the protons, is going to be a proton sink, right? Oops. It comes to this junction area to make water. And then because the proton's in here left, you're left with a hydroxide ion to pair with the sodium ion. And we've substantiated this, so MD simulation's been running low on time, so I'm going to skip over that. But now what we wanted to do was exploit this pH inversion effect. So we use this dilithium iron phosphide electrode that has a high affinity for lithium. We use this bipolar membrane. And so we feed in this solution of lithium brine solution, competing cations. We run charge mode, so we generate protons here. This selective electrode here, the lithium ions intercalated in it, the other ions don't. We're left with those other ions and some HCl solution. Then when we release the lithium ions from this selective electrode material, we run this BPM in forward bias mode. The protons come to meet up with the hydroxide, make water, and then we get a hydroxide that's left behind in this solution. We get lithium hydroxide, which is that desired material that battery manufacturers want to use. So in a single electrochemical device, we can do separation and conversion of lithium from brines to lithium hydroxide. So that was really exciting. We filed a patent on this. We have a paper under review. We did some feed solutions of mixtures of lithium and sodium and lithium and magnesium, and we see very, much more higher removal efficiency for lithium versus sodium and magnesium. We did model geothermal brines here. So here we have lithium in much smaller concentration than sodium, magnesium, potassium, and calcium. And then, after 8 cycles, you can see that most of our solution contains lithium, a little sodium, and a little magnesium, and doesn't contain any potassium or calcium. So this approach seems to work pretty well. And so what we're doing, right, is taking a selective electrode and a bipolar membrane working cooperatively to enable selective ion separation. So finally, I'll tell you real quickly about phosphorus. So we talked about agricultural runoff earlier in the talks. We have these nitrogen phosphorus-based fertilizers, excess application of it. You get nitrate, phosphate waste coming into receiving water, leads to eutrophication, algae blooms, water quality deterioration. And this work by people at UCLA, I don't know why they did this, but they used the cation exchange membrane as opposed to an anion exchange membrane. The cation exchange membrane should reject anions because of dominant exclusion. But when they put the phosphate particles in here, manganese oxide particles here in this composite membrane, mixed matrix membrane, they observed much greater phosphate transport from one compartment to another. And they didn't evaluate this in an electrochemical unit. So what we wanted to do is put this in an AEM, which is an anion exchange material, would take phosphate anions, and we wanted to do this in an electrochemical unit. And so we looked at a case where we had traditional flow by MCDI. This is where we made a membrane with those particles added to the AEM, mixed matrix AEM with the CEM, and then where we put a bipolar membrane. And so this bipolar membrane is going to make this stream alkaline during charging, and then that will deprotonate the phosphate salts, and then this membrane has a high affinity for phosphate to enable the selective separation. So we studied some other things in there like charge mode, different concentrations of the manganese oxide content in the AEM. I can't elaborate on those in details. What's really important is that when you incorporate the manganese oxide into the AEM, and then you ion exchange the chloride counterion in the AEM material with phosphate or hydrogen phosphate, you're also ion exchanging the manganese to manganese phosphate. And we sort of confirmed this through XRD. These are our composite membrane. Looks jet black. This is electron micrograph showing the incorporation of the particles into the membrane host. And what we're interested in here is this phosphate removal and selectivity. So we had about 10 times more chloride than phosphate in solution. So this is the pristine material. So with the composite material, you can see right here, this red line is much higher than the one with the pristine material. So the incorporation of this manganese oxide particles in the AEM is facilitating greater phosphate to chloride selectivity. And then it's also increasing the removal efficiency. So, as we apply more voltage to try to drive more of the ions out of solution. We get more phosphate uptake. It does come at the expense of the selectivity. So that's a balance that you have to do in the separation. So if you really want to just get one ion over another, you might have to dial back the voltage. It's just you're not going to remove as many ions from the system with a lower cell voltage. Again, working with Revity, a collaborator of ours, she did some electronic structure calculations showing that this hydrogen phosphate has a very favorable absorption energy on the manganese oxide particles compared to the pristine AEM, and that the chloride absorption is more favorable on the pristine AEM than the manganese oxide. And so that's sort of what enables that selective separation. So this is our best data, my last result slide. We're able to get a selectivity value as high as 1.1 at a 1.5 voltage while still removing 30% of the phosphate from the solution. And we're able to do this, with pretty good stability over 30 cycles. But in practice, of course, you have to do it over many, many more cycles and actually do it with not model solutions, but real solutions. So electrochemical separations will play a prominent role in sustainability, as it will help facilitate the energy transition, critical minerals, and environmental remediation. How do we recover nutrients from waste streams so we don't have, deterioration of our natural water bodies? PFAS removal I talked about earlier on, and heavy metal removal is really important. I didn't talk about gas separation today, but that's an area we work in. So we think CO2 is really important as well. I think the field needs to evolve. Most mature platforms today have been deployed in desalination with the aim to just, make potable water, ultra pure water, just remove all the ions from the liquid mixtures. We have no discrimination of one ion over another. And this is not what we want. But I think if you can have selective electrodes, mixed matrix membranes, in situ pH adjustment, new cell architectures like shock EV, these things can work cooperatively to enable electrochemical separations for selective separations. So with that, I'd like to thank you for your attention, and I'm happy to answer any questions.
Wow, thanks, Chris. That was a very comprehensive presentation on electrochemical separations, starting from the basics into the deep theory and back into applications. So I think everybody got a good sense of, how broad the field is. Now we can take some questions. You can either message me here or perhaps you can raise your hand. And while people are kind of filtering questions out, one question I had was back actually on your slide 42, if you could go back. You had mentioned this idea that you were able to do the electrochemical separations and basically have this all-in-one device to create the lithium hydroxide for use or battery manufacturers. I mean, at what scale did you do this? I mean, this is lab scale?
Lab scale, of course, and there's a lot of things that still need to be done. So the geometric area of the cell is 25 centimeters squared. I'd have to go back to the paper to look at the flow rate, but it's more like a proof of concept, proof of an idea. And it was all based on like that observation, like, hey, why when we were doing the discharge, why are we making lithium hydroxide? And I think we were just talking one day, well, what if we captured the lithium and then, on the discharge, the ion that we're releasing, like we're making this base solution. Now we have the hydroxide salt. The one challenge right now is the concentration, I think is, I don't know, maybe 35, 40 ppm. It's only like around 10 to 100 ppm of concentration of lithium hydroxide. We think we can do better by seeding some lithium hydroxide here first to reduce the ohmic resistance. But, with multiple cycles, you continue to increase the lithium hydroxide concentration. And of course, if you had multiple cells and larger cells, you'd be able to get the much higher concentrations that people would be interested in. So, so a lot of work to do in that area, but very good question. Thank you.
Yeah, I mean, it just seems like, you hit a point where we're ramping up on so many electrochemical devices, and I think not much is said, or it's not really broadcast widely about the separations that we're not taking advantage of. So, your presentation really hit that. We do have
thanks. That was the takeaway message. Like,
yeah,
I want more people to work in this area. And there's people like other people I mentioned throughout my talk. So if that's the one takeaway today, I hope that was it. Thank you.
Yeah, definitely. I mean, I felt it. And okay, so we have one question. We have a person who has asked, how do you actually make the in situ measurements of solution pH? So were you like pulling
We
out
have a
a
that we have
device?
a downstream. We have conductivity and pH probes. Um, so like right out the effluent, that's where we're measuring the pH. So we're measuring the pH of the effluent. We're not making like any local measurement within this process chamber, of course, but it's more of a bulk measurement in the effluent stream.
Got it.
But it's
You,
it's it's an inline one, so it's real time data, right? Like
right,
I think I have the pH data versus time. Yeah, so you can see it, right?
right. Okay. One question, follow-up question was, did you study the effect of flow rate in these systems, like because of the mixing effect, I guess, as you flow through?
Yeah, that's a great question. Not extensively. So I think this one here, so we call it residence time. So the residence time, how long the solution sort of sits within this cell is dependent upon the flow rate, right? So if you take the volume divided by the flow rate, right, it'll give you the residence time.
Right,
And what we notice is that the extent of pH change, right, goes up with larger residence time, lower flow rates. So it's a trade-off, right? Like you might get more selective separation, like greater ion uptake in the electrode, or more pH adjustment by letting the solution sit longer within the cell, but that will inhibit how much volume you can process, right? So
right.
so yeah, we haven't studied it extensively, but we do know that it matters.
Got it. Thank you. We have Philip Hicks has raised his hand. Um, I think you can unmute yourself and actually ask the question.
Yeah, cool. Can you hear me okay?
Yes.
Mhm.
Great. Hey, yeah, Chris, thanks so much. Awesome presentation. I am pretty new to the field of electrochemical separations, and I'm curious if you have any resources that you would recommend. I think you had some books maybe listed at the end there, but like good resources that go over the fundamentals of various types of ion exchange membranes,
Mm.
some of the other kind of fundamentals of stuff that you talked about. I think probably nutrient recovery and water processing are my main interest, but just generally, if you have any recommendations on good resources, that'd be great.
Yeah, I would. I don't know if you're welcome to email me for like I could answer that question a lot of different ways, but
Sure.
one, I would encourage you to email me, and I can definitely share resources I have. So one I talked about early on in my talk about this ECS interface article here that came out this last spring. So we have a chalkboard issue article that I authored that talks sort of a little more in depth about the broad areas and the modes of action for separations. You mentioned ion exchange membranes, and like there are some really great textbooks, like older textbooks out there, written by two heroes in the field, a guy from Japan, Sada, and a guy from Germany, Strothman. And they wrote, yeah, and I mean, they were like leaders in their field starting in like the 60s, like through the 90s, like just all the fundamental aspects of ion exchange membranes for electrodialysis, which is like taking all the ions out of water. But if you start there, like, and understand like the basic electrochemistry and mechanisms, that is useful for doing then things more complex, which is what the field is trying to do now, which is selective separations. But when it comes to selective electrochemical separations, I feel like right now, like there isn't like, I mean, there was a nice chemical reviews article by Xiao Su and Martin Bazant. Mo wrote that article. Uh, that's also pretty good. I can definitely contact me. I'll share some things for you.
Yeah, I'd appreciate that. Thank you.
All right. We have a Dylan Schultz.
Okay. Hey, I had two questions. One of which was a follow-up from the pH question earlier, which is, shouldn't you, because you have an anion and cation exchange membranes, get very, very wildly different pHs locally in the cation exchange membrane and anion exchange membrane, and also at the electrodes? It seems like the local pH environment should be anything but uniform in this case, to me. And the other one I wanted to ask is I come more from the fuel cells and and electrolysis fields. I wanted to ask if you have any thoughts on the kind of the conditioning behavior for membranes, because I've gone to conferences and so on. No one seems to have the same conditioning behavior for anion or cation exchange membranes. All of them are completely convinced that they understand why you need the conditioning, but all of them are different reasons. So I was wondering if you have any thoughts there.
Yeah, it's a great question. So I don't know if I have a really good answer for your first question, but I definitely think in the world of fuel cell and electrocatalysis, like I saw a very nice presentation by Lindsay Seitz and her team at AICHE a year ago, where they're using a rotating ring disc electrode to study like the local pH effect, like on OER, right? And the local pH will be different than, say, the bulk pH, right? And there will be pH gradients, like, across the geometric area, as well as maybe even across the membrane. So I think that's a very good point, well taken. The way we have our experimental setup, we just can't probe right now those type of local pH values in an operating cell. But I think if somebody could do that, that would be fantastic. So like, again, some people who are doing it, they're doing it in a rotating disc electrode, right? It's an under very idealized case, but not very practical to a device situation. The other question on membrane conditioning, in our work, the phosphate removal, we knew this from a different project that we had done, that it was very hard to get phosphate through the AEM at first. Like if you just stuck the AEM in the chloride form in the cell and fed it in a phosphate solution like sodium phosphate, we get very little phosphate removal. And my postdoc, who synthesized the polyterphenyl alkyline anion exchange membrane, I don't know how he came up with it. He just let the cell sit like an ion exchange, like with a phosphate solution overnight. And then the device worked much better for phosphate removal. And so what we realized is that, okay, you need to ion exchange to the desired ion that you want to move before running the cell. So that's not like a very, more of like a serendipitous effect of like exchanging, of processing the membrane, but we found out that works. And then,
No, that makes a lot of sense, actually.
Yeah, like the thing with like, I'm from the fuel cell electrolysis world, so like I remember breaking in fuel cell MEAs for good fuel cell performance, and there's a lot of things going on. Like Yusung Kim, maybe not on the membrane side, but he used to show some work, I think Christina Johnson, like the solvent you use for the ionomer and the binder can affect the polymer relaxation, like the rearrangement of the polymer chains and microstructure, and that can affect properties. And I think it's an underappreciated area of science. Like I think what we need to do is use advanced metrology for like different whatever conditioning or procedures, and really understand what is going on from the structure standpoint within these materials.
Yeah. Okay, thanks. That was quite helpful. Thank you.
Great. So I think we'll take one last question, and then we'll close the session. Peter?
Yeah, Christoph, thank you for the nice talk. I was wondering, maybe perhaps I missed it, the origin of the enhanced separation when you added manganese oxide. Towards the end of the lecture, you did show this impressive result. What is the fundamental origin for this? Can you explain?
Really good question. It's just all we know is this manganese oxide has an affinity for phosphate, and what we know is that the manganese oxide through the ion exchange through the XRD is making manganese phosphate. So even there itself, the manganese seems to have some affinity for going from a manganese oxide to a manganese phosphate, and then these electronic structure calculations just shows like for a model manganese oxide system, placed with a phosphate, there's a large thermodynamic affinity for adsorption. If we look at the phosphate affinity for the quaternary ammonium on the anion exchange material, it doesn't have a lot of very large thermodynamic efficiency, even though that electrostatic interaction. Now, what's causing this large thermodynamic efficiency? What about manganese that does that? I don't have a good answer to that. I think that's something we need to look into. So,
Okay, thank you very much. Yeah, thanks. Yeah.
Awesome. Actually, just one quick question, almost comment is we have a person here interested in I think it's this type of system for sulfate and phosphate removal from industrial process streams. How would you get started in trying this out? I suppose you'd have to send them membranes.
yeah, again, I'm happy to talk, for anybody, right, who's here today, I don't know if you can put my email in the chat or maybe you can put it on the webinar site or something. But if you just go to Argonne website and look up Christopher Argus, you should be able to find me. How would you get started? Good question. So, I mean, I think what I'd like to see for this area is have industrial players like you, like come to us. Yeah. What exact problems are you working on in phosphate and sulfate removal? What are the feed compositions? Are there other things in the process stream? And then, think about how we could work together. So, for the flow by MCDI architectures, I only know one commercial company in the US called Motea that makes those systems. They do the hardware manufacturing for it. But then what we sort of showed is that you had a membrane material innovation, and that membrane's not commercially on the market. So, we would have to take something that we've developed in the lab and then, how do we do that whole entrepreneurial thing of filing patents and scaling it up and commercializing it? Is there a good market business need for it to justify its cost? I think, a lot of work has to be done in that space.
Right. All right. Well, Chris, thank you for your expertise and sharing your knowledge to everybody here. And everybody, thank you for attending. We have recorded the video, so we will eventually get it up on our website for you to go through again. I mean, it was pretty good stuff in the center there with a lot of the activity coefficients. But yes, I think with that, we'll close out this session. Thanks for joining, and we'll see you next time.
Yeah, thank you. Thank you, Jerome. Thank you, Gamry. And thanks for everybody for attending. Have a great day. Thank you.
Yep. Perfect.
Okay. Thank you and farewell.